Okay, I hope you can hear me. So Hilding Elmqvist from Sweden, and it's great to be here talking about a domain-specific extension to Julia. We call it Modia, and it's for modeling and simulation. So system modeling, not CFD, but really system-wide models. And I will explain a little bit about the background to the topic and why we are doing this. And so first a rationale for this project. And I should also say that so far it's only 3 people involved. More people are coming into it, but so it's a small effort so far. A rationale for this and background, and then I will talk about this, the Modia language extension, by giving some examples of what you can do, and talk about the prototype work we have, so the implementation in Julia. So I come from a background with a language called Modelica. I started this design effort in '96 actually, so for systems modeling. So there are quite a few tools now supporting this language. And a little bit specific with this language is that it's based on equations. So you actually enter equations. So expression equals expression to capture physical know-how about physics. So it's object-oriented and so on. And typically also there is an associated graphic. So you do these kind of diagrams, as you can see. So an electrical circuit, for example, some fluid system or some gearboxes and rotational stuff. Okay, so this is Modelica language. And the important thing is that it's ordinary differential equations and algebraic equations. These are what we're using. So usually called DAE, so differential algebraic equations. And which means that you cannot use just an ODE solver because there is a machinery that you need to implement to transform this DAE to a suitable form for evaluation. Okay, so why this Modia? And one thing what happened was that the evolution of the Modelica language stopped because there were many tools implementing everything and didn't want really to have too much of additional features into the language. So then we figured out that it's better to have an experimental language. And of course, it would also be good to have reference implementations of these algorithms that I will talk about, symbolic algorithms, structural algorithms. Another thing that is good with Julia, the coupling to Julia, is that in Modelica there is this equation-based language, but also a language to describe algorithms, so describing functions. And we didn't want to extend that because of course it's a huge effort. So that is why we started to work with Julia. So now the first model then in Modia. So you see a simple model in Modelica and how the similar structure is used in Julia and Modia. So Modia is a set of macros. So there is a model macro saying that, okay, this model consists of some variable declarations and some equations. And you see it's equations, really. I was extremely happy, I must say, when I discovered that the parser of Julia allowed me to parse expression equal expression. That was perfect. Okay, so this is how you can describe a very simple system. Of course, it's trivial to solve for the derivative of x and integrate this with an ODE solver. But in general, it's much more complex. Now, typically what you want to do is to connect subsystems according to the physical laws for connections. So what we do is to define a connector, or in this case for an electrical component, a resistor, we would define a pin that would be two variables, the voltage and the current. And we also state that current is a little bit special. So because we set a flow attribute, it means that when you connect several electrical components together, the current, the flow, is actually summed to zero. Thus, this semantic rule is also used for energy balances and mass flows and for torques and forces. It's a similar rule. So that is a very important semantic rule of how to treat a variable and how to treat associated couplings. Now, when you have such a pin, you can then declare two instances of it corresponding to these two pins of a resistor, and you can add some equations and then make a resistor out of it. So of course then what you need to do is to define a parameter for the resistance and then add Ohm's law to describe the behavior of this component. So that is how you typically build a library of components. So this is built into libraries that you can reuse. But then how to reuse it? Okay. If you want to have a little circuit like a low-pass filter, you declare the components in this way, and then you say what pins are connected together in this connect statement. So there is a special interpretation of that. Of course, so that happens when we expand the model macro, of course, and we need to interpret this connect statement in a special way. But, of course, this is not a way. If you would model an electrical circuit in this way, when you have hundreds of components, it doesn't work because it's too tedious and error prone. So, of course, what you want to have is some kind of diagram that shows the topology of your circuit. Now, what we have done in addition to this Modia project is to create a web app. And it's just starting. It's a bachelor thesis project, and I will show a little video how you work, so how you connect those pins, and in this way we also use an automatic layout and routing package in JavaScript to actually get this diagram. Then we can insert a component, a spring in this case, and yeah, that is the one. And how to connect these, duplicate the inertia, connect this as well, and then setting parameters. So there is a dialog for setting the parameters to make specializations of these components. And then you can go to the simulation tab and simulate. So then using remote procedure calls to the server running the Julia code, the Julia compiler and the Julia runtime system for solving these equations. Now, I will show a short video to also indicate just that, yes, since we have a web app, you can actually use it on your phone. And the scenario the student got was, what if you would like to do modeling and simulation while you were taken home by your autonomous car? And why not? I mean, it would be possible, of course, as shown here. I don't know if it's feasible, not yet, but in a couple of years. So I think it was a good topic for the student. Okay, but now back to what happens with Modia. So since we're dealing, these variables are time-varying quantities, so you need to solve for a trajectory for the behavior. And a variable then has certain attributes in this, such as this. I mean, of course, the type size, the actual value, unit, mean and max values. So typically, to make the models more robust, you would declare these kind of things. And also start values, since you need to initialize the equations in this way. So that is typically the attributes, and then you can, of course, declare a variable like this. You can specify that you want a specific array type. If it's a matrix, specify the size if you like. In certain cases, this can be inferred, but of course, in the libraries we usually put it in most cases, to declare the sizes and units and types. And in particular, you see that I use the siunits.jl package to have SI units as well, so you can really make unit checking of your equations. So for example, this is type declaration corresponding to this. I will not go through the details, but for example, a position has the type of the variable is meter, and then I can say that a free vector of positions that is used for multi-body modeling has a size of 3 elements like this. There's also special properties for rotation matrices built in order to handle multi-body systems. So multi-body modeling you can do in this case in this way. You have then a different kind of connector called frame. So for multi-body you have the position, of course, in space, in 3D space, the rotation as a matrix, then a 3D matrix, and the forces and torques acting in this point. So that is how you couple parts of the multi-body system. I have one example here for a revolute joint, how you would model that. So you see the equations of this form. So it's matrix and vector equations that are input. And also there are special techniques needed to handle DIEs. So there is something called DIE index, and you need to make a reduction of that before you numerically solve the equations. Which means that in this case, this equation here needs to be differentiated versus time. Okay, in some cases, however, you want to have generic elements like a switch, taking 2 inputs and then you just switch and the output should be the same. And you can then just say it's a variable and the types are deduced. The types and the sizes and the units are deduced by the pre-processing made in Modia. We do handle discontinuities like state events. Typically, a numerical solver want to have a crossing function when something significant is happening. We mark this by a function positive, so if it's positive then 0 or else variable s, and this is one way to describe an ideal characteristic of a diode, for example. And then this crossing, this event here is detected with high precision. We are working also on synchronous controllers. It's a special semantics for how to couple control systems in a safe way to physical plants. I will not go into details. I just want to mention that this is also done. And then you need to infer also the clock. So each variable and each equation has an associated clock, and you cannot mix them in an arbitrary way. So it's actually checking that the variables and the clocks have and the equations have consistent clocks. That is also done in Modelica, so it's nothing new. We are re-implementing this now. But there are things that cannot be done in Modelica, and this is one example here. The constructor could be an if-else end clause, for example, in this way, to either select gearbox of type 1 or gearbox of type 2. So you can use Julia's if expressions to select what kind of instance do you want, what kind of class do you want to instantiate. You can even have a vector of models, for example, and then you select out of an array which one to instantiate. This is things that we have discussed in the Modelica community, but now we could start to experiment with it. Even more powerful is the ability to do just-in-time compilation. Because if you have a clutch like this in a rotational scheme, so you in an automatic gearbox, for example, you have lots of clutches, and you say that you want to have an ideal clutch, then the equations are changing. So either, if it's not engaged, the torques to the neighbors are 0. Otherwise, the angular velocities are constrained to be the same, and the torque sum to 0. So it's different set of equations. And since the equations are changing in this drastic way, the symbolic treatment of the equation needs to be done because this DAE index is changing. So the symbolic and structural treatment is redone when such a major event is happening. And at that time, of course, we generate a new function to evaluate the residuals of the DAE, and we feed it to the compiler. Just-in-time compilation is utilized, and of course we have caching. So if we return to the same mode, saying that okay, we did already a while ago do this symbolic and structural transformation, and we have the function already compiled, we can reuse it. This is completely new, and it's also needed in new kinds of scenarios for modeling and simulation. In particular, since we want to model things that also break. I mean, what happens if something breaks? How will the control systems and the redundancy of the system handle such a situation? And when something breaks, we need to do this, redo the structural transformations. So this is important. Another thing, of course, as I said, we need to we want to utilize the built-in function, algorithmic capabilities of Julia. So I have just one example here, how if you have a set of balls like a billiard table, you would like to have a function that calculates the sum of the forces between all the balls when they collide. This is one way to do it. And of course you can provide an anonymous function for the force law. This is a spring damper notation, the spring damper force law that is provided. And also we have a capability to say that, okay, give me the positions of all the balls as a vector, and that is fed to this get force function. So this is just one example showing what you can do with mixing Modia and Julia. Of course, I mean, to do this efficient, of course, for many objects, we need to have octrees and so on. So I know this is an order n squared algorithm, but it's just for the purpose of illustration. Okay, so how to simulate a model? So we need to instantiate the model. So creating these sets of variables and sets of equations. And then we structurally analyze. This is just illustrating. We have the variables up here and the equations. So these are the component equations. And down here are the connection equations. So that is the structure of our problem. It's a square matrix, and if we view it as matrix, as I do here. Of course, internally we have better data structures than that. Based on that, we can look for these hidden constraints that will force us to differentiate certain equations. So that is done by a structural algorithm. It's famous in our community. It's Pantelides algorithm. After that, we can sort the equations into execution order, and then solving for the unknowns and generate the code and then symbolically solve it. The BLT, the block lower triangular form of the equation. So it typically gives a execution order in most cases, but then we find that there is a mutual dependency among a small set of equations. And there is an algorithm by Tarjan to find the strongly connected components that is utilized in this case. And of course then for this we need to calculate the residuals. There are also other graph theoretical algorithms we utilize called tearing, for example, to reduce this system of equations to as small as possible. And this strongly connected component algorithm, I just included it as one. I mean, it's taken from a famous paper and of course recoded in Julia. So it's a lot of these structural analysis algorithms that has been re-implemented in Julia, and also for symbolic manipulation and solving matrix equations and so on. And of course, all of this is based on this wonderful meta-programming feature. So it's two things, of course. Expression equals expression as being able to pass that through the parser of Julia. That was fantastic. But of course, meta-programming is even more powerful, because then we can re-implement all the algorithms. And in this case, of course, I have just a silly example where I have an equation of this form and I do it explicitly solve to generate a solution when x is unknown. Of course, this is automatically done. And then, of course, just evaluating it and yeah, it is used a lot in Modia implementation. So as a summary then, it's Modelica-like language, but more powerful and simpler. On the other hand, it's more powerful in some areas, but of course, so far it's weaker in some areas. I shouldn't overstate it. And then the algorithmic part, to use Julia functions, much more powerful than Modelica functions. We didn't have to implement a Modia parser. We use that for the equations and the models, the model declarations. And then, as I said, we can use the same language to implement all the structural and symbolic algorithms. We use sundials then, actually an extension we are working on, and that will soon be published as well, how to handle overdetermined array DIEs. So we are going through a lot of algorithms that has been utilized in the Modelica community and trying to generalize, and of course, some of this has already been published, and of course, just-in-time compilation is extremely important. So the next immediate steps, we need to expand the test suite. We have some problems with code generation of big functions, actually, because all these, I mean, I tested 1 million equations, for example, and then it's a really big function that gets generated. And of course, the compiler couldn't cope with that. So and we need to split it up in pieces and so on. So there are these kind of things in order to make it robust. For Modelica tools, typically can handle maybe 5 million equations or so. We need to set up automatic testing. I tried to set up coverage. I didn't manage because I have a Windows computer, I think. So I need some help in these areas, and of course make a package out of this. And we also need to make a proper web server. For the moment, I'm sorry to say, I used a simple JSON RPC server in Python and then called Julia from Python. There must be better ways, of course. Please help me. Okay, and yeah, we have this hackathon, so please, if there are some people that would like to help out, sit down and discuss how to proceed, I would be happy for that. Because we have not released it yet, so there is a website with some references so far, so there are some references to the work, but we need to clean it up and, as I said, make it more robust, have more test cases and so on, before we put it on GitHub. So that is the plan. That's all. Thank you.